All right, let's do some integration by parts. This is actually section 8.2, integration by parts. Now, I have this sheet here that's also uploaded in Canvas, so you can use it that way too. But I like to use this as a guide. Will you be able to use this on e-quizzes or tests? No, right? But it's just a way, just a learning guide to help us. So your book uses, uses u as the variable. I have a tendency to use f of x and g of x as that variable. So whenever we're looking at this integration by parts, here is the function notation. Here is the u and v notation, okay? Exact same thing. They're literally exactly the same thing. I like to use the function notation because it shows what it is a little bit better, so it makes more sense in my mind instead of the u, dv, u, v, v, du, although that is all super valid and it's less variables that you're looking at. This part 2 down here is just the definite integrals. So you're just plugging values in. You're just using normal old fundamental theorem of calculus. Okay. Now here's the kicker whenever it comes to integration by parts. There's a couple things to look at. Things number 1, defining characteristics. You know I like to say that. These are multiplied functions. All right. You have things that are multiplied together. That's what you're looking for. If you can't do a u sub, right? Because u sub is always our go-to method. If I can't do a u sub or anything that we already know with algebraic manipulation, then I'm looking here in terms of integration by parts. Multiplication. That's my tip-off that we're looking at integration by parts. So this first part here is the pattern that you see. I have two things that are multiplied together. Right, so this g prime here is going to have my differential with it. Just like you have your differential right here of dv, that just means that that's the differential. I have f of x and g prime of x. Two things that are multiplied together. Then my solution to this is that. So it's an algorithm. Once you identify integration by parts, here is the algorithm and the solution in order to perform integration by parts. You take your f of x and your g of x, right? Minus, those come out of the integral, minus, and then you integrate g of x and f prime of x. We'll do examples. So this is just the pattern of integration by parts. That's what you actually do. All right. So here, p of x, I'm going to squeeze this back in just a little bit more. P of x is a polynomial. I have it up there at the top. But you're also looking for a lot of polynomials. If you have some polynomial times your e of x, the thing about integration by parts is you have to decide what is your f of x and what is your g prime of x. All right? They're not always in that order. Sometimes you want to use the first thing as your g prime with the differential. It just depends on what it is that you're looking at. If you have a polynomial, typically that is going to be your f of x. The time that it doesn't happen is if you have natural log. No matter what, natural log will always be that f of x. And the reason for that is because you have to have integration by parts and even to do the antiderivative of it, okay? So anytime you have natural log, that's always going to be that f of x. All right? The other thing, here with 5 or 6, look what's happening with these two. If you try to take derivatives and antiderivatives here of this e to the x or sine or cosine, you're going to spin in circles. So in examples 5 and 6, you're just going to apply integration by parts twice in order to come back around, and we will do an example of that. Okay? All right. And so just like it says here, 1, 3, and 4, you're going to apply integration by parts by whatever the degree of your polynomial is. Because my goal here, let me squeeze this back down. My goal here is I right now have something that I can't take an integral of. So if I have a polynomial, I have to get rid of those exponents of that polynomial so that it's something that I can actually work with. Okay. All right. So here I just wanted you to see there's the basics of what it is that we're doing. Now let's work an example so you can see this in play. Now remember, you don't get any of this stuff on your quizzes and tests, right? You have to practice this enough so that you know how to play this. All right, here's example 1. I would like to integrate x times e to the x dx. Can I do a u sub? That's always what we go to, right? Always, always, always. No, we can't do a u sub. Good, good, good. So if I'm looking at this and I want to split this up, I've got my polynomial, which is just an x in this instance, and my e to the x. Let's swing it back. If you've got a polynomial with an e to the x, your polynomial is going to be that f of x. All right? Now here's how we are going to set this up. Automatically set up your f of x and your g of x. Lies, lies. That's lies. F prime of x. Because I put my g of x over here because it's the pattern. G prime of x. Remember, the information you are getting out of this is this f of x and this g prime of x. So, oops, I'm going to go blue. This is my f of x. This is my g prime of x. E to the x dx. Keep that differential on there. That's showing that that's that derivative. That's where my differential comes from. Then I'm going to do the derivative of x is 1 dx. Don't forget your differential. It's important. Remember that differential. Now, whenever I start with my derivative and I go back, this is where we're going to take an antiderivative. Well, the antiderivative of e to the x is just e to the x. All right? Your notation is important. That's why I have been hounding you about your notation. In this type of problem with integration by parts, you're going to be taking derivatives and antiderivatives in the same problem, and you need to know what it is you're looking at. All right? So our formula here, when I integrate, I've got f of x, g prime of x, and then this is going to be f of x times g of x minus the integral of g of x and f prime of x. So this is what it looks like. These go to the outside. These go inside my integration. That's what that is. That's why I set this up like this, so you can spatially see where all of this stuff is going to work. So I now have x, e to the x. Neither one of them have a differential because neither one of them are prime. There is no differential there. These come outside of my integral. Minus my g of x, which is e to the x, and my differential now is dx, because that's my f prime of x. Do you see that? On the outside, x times e to the x, minus my pattern has g of x, and then this dx. Now here's my question for you. Does this g prime of x make a comeback in my formula? It does not. The sole purpose of this g prime is simply so you can get the antiderivative, which we use a lot. We use twice, right? Out here and in here. Now, which happened because my goal is to get something I can now integrate, I've got x e to the x, and then the antiderivative here is just e to the x. It's an indefinite integral, so you put plus c, and that's it. Right? The big deal here is basically knowing the formula, essentially, that goes with this. All right, let's do some more. This practice makes an impact here, so let's do some more. Okay, I'm going to scoot this up a little bit. Let's look at example 2. I have the integral of x sine of x dx. Got our polynomial again. I cannot do a u sub. I've got two things that are multiplied together. Yep, so you come over here and you've got f of x, f prime of x, g of x, and g prime of x. This is how I set this up. Some people set it up just a little bit differently and it still works. As long as your pattern is the same and you're following the formula, that's up to you. All right? Okay, so I know that this is my polynomial and this is my g prime. So I've got x and sine of x dx. I'm going to say it again. Put that differential in there. You have this differential, use it. All right? Use that differential. Now the antiderivative of sine, right? Because I'm going backwards, so my antiderivative of sine to get g of x. Yes, good. If I'm looking at this, it's a negative cosine x. And then the derivative of x is just dx. All right? So across and diagonal, I am going to have negative x cosine x minus my integral here. But whenever I look at that integral, I have negative cosine. So we're going to pull that over here and make it a plus, right? Cosine x dx. And then we can take the antiderivative of cosine all day long. Negative x cosine x plus the sine of x plus c, and that's our answer. Sometimes in your book or in the notes, they will rearrange this so that you can have sine of x minus x cosine x. That way you just don't have a negative out front. Doesn't matter. All right? I would take either one. It doesn't matter, but I just want to point that out to you in case you're looking at that. This is about recognizing patterns and being able to plug in the integration by parts formula. Okay, we're going to practice a whole lot more. So here we go.